Hey, you Evan. Thanks so much for coming along to the webinar. As always, got my usual crew, doing well. Got 7 people. I've got 2 things playing at once. Right, guys. Okay, so we're going to be having a look at industrial chemistry today, and it's been really nice to spend the last 30 minutes or so having a look through your specification and really taking it to pieces. And I've done the usual thing of taking your spec points. We're going to have a look all the way through what you're expected to know. I will also try to focus on picking up those other additional processes which they have now deleted, but they're useful to have. And I'll explain why when I cover each one of them. Okay, so what I'm going to do is share my screen as normal and drop us into the webinar. Okay, so I hope you've all managed to get your preliminary work sorted. Nice to say hello to the usual people. Daniel, nice to have you here. Nice to see you, Rumin, Lara, Winkit, Sarah, Dana, Karen, nice to see you all. Thanks for coming along, guys. Right, okay. So my usual thing in terms of learning objectives. I do also want to mention a couple of understands in there as well, but the key things really here are for industrial chemistry is making sure that you guys are aware of the exact facts that you're going to be asked to quote in your GCSE exams and the ones they can definitively ask you about. So know the industrial reactions to learn, be able to explain conditions used for each one of those industrial processes, and also to know other useful reactions. These are the ones that have kind of subsequently been erased from the syllabus. But as you'll see from the spec points, they can still do sneaky questions, and it's definitely worthwhile having those kind of in your repertoire of knowledge. So I've taken your spec points and I've hacked it up in order to pull out these bits and pieces that you need. So the first one is a metal extraction. So it's nice to see that the metal extraction processes are still there, but they're not going to specifically ask you for conditions that they need. I'm going to look at the electrolysis of aluminium in this webinar specifically, and I might even do a little bit of the blast furnace. But what I wanted just to highlight here is be able to comment on metal extraction processes, be able to comment given appropriate information. Now, I don't trust Edexcel as far as I can throw them, and I know what they're going to do is they're still going to lump in these industrial metal extraction processes, even though they won't be asking for specific details. They're going to be asking you some questions on them, and it's nice just to confirm those kind of points. And it's nice to also see that the detailed knowledge of the processes used in the extractions for specific metals is not required. So they're not going to ask you to quote them. What they're going to ask you to do is they're going to give you them and they're going to ask you to explain it. So I'm wary of that particular point. The next one is describe how the industrial process of fractional distillation of crude oil occurs and how we separate it into the fractions. So what I also want to point out here is due to the reduction of industrial processes they're expecting you to know, what they're going to do is they're going to amp up the questions that they're asking regarding these ones. So there is some nice kind of outcomes of this. And the first one is that you pretty much can guarantee which ones are going to be appearing on your test papers. You've got paper 1 and paper 2, and you can clearly see that the paper 1 is going to be focusing on fractional distillation. So you can pretty much guarantee this one to be in your paper 1. And that's really nice. The next bit is the cracking of alkanes. And again, this is going to be heavy paper 1 because this is for dual and triple. Now, the next one, of course, is the process of creating ethanol. And it's interesting that they've decided to keep this one. And I'm going to show you a couple of questions regarding those and some of the practical diagrams that have appeared over the last few years. And they're really hitting home on this organic preparations in terms of their industrial processes. And every single one of these is going to be on your paper too. So I think that's actually kind of nice because it pretty much guarantees them to appear rather than having 5 or 6 industrial processes you're expected to be able to quote temperatures and pressures for. What they're doing is they're simply cutting it down, and so you can pretty much be sure of what's going to be on our paper. Now, I'm also going to just quickly mention equilibriums as well, because the equilibriums which have been removed, of course, are the Haber process, which has now been removed, which is nice. And the second one is the contact process, which has now been removed. Now, the reason why I don't want to delete them from my webinar is because in your equilibrium specification points, what they're going to do is they're going to ask you about these. And they're not going to ask you for the specifics for the industrial processes, but they're simply going to ask you them in regards to equilibrium. This now becomes the heavy focus rather than can you regurgitate the conditions that are done in industry. Question about cracking. When it splits into shorter chains and alkenes, can you figure out what alkenes and alkenes it splits into? Kayan, they're gonna give you that. I will show you a question, and I'll go through a question with you and show you how they're gonna specify this in your exam. Wow, I can see you write new stuff on my copy of your notes. Laura, I shared my notes, my OneNote document with Laura, and it's updating in real time, which is rather entertaining. Okay, so what I'm going to try and do is I'm going to try and keep this in an orderly fashion. I'm starting to get better at being able to organize my notes in lessons. So I'm just going to scroll across over to this way and just quickly do metal extraction. So the metal extractions have now been removed. So this is kind of the first part of industrial chemistry that used to be there. You used to, but in a not exam context, how would people predict the product? Not in an exam context. Cracking is a very complicated process, and it's now got a huge amount of detail in it because there's now a huge, there's a massively varied types of cracking that are available. So in GCSE, you learn about catalytic cracking, and now there is thermal cracking and flash cracking and slow cracking processes, all with a variety of conditions, which actually gives you different products. But you're not going to be asked in those kind of details. So, okay, in terms of metal extraction, the two ones I want to quickly talk about is I just want to quickly talk about the blast furnace, and I want to talk about electrolysis of our blast furnace. I'm going to put it into the iron context. Now, I've done this, of course, in part in my metal extraction webinar. So, but it's nice to recap this and put it into an industrial setting. I'm going to then do electrolysis of aluminium. So, okay. Now, just to kind of group these, there are some key facts which kind of can be overlaid onto all metal extraction processes. So all industrial metal extraction, all industrial, and I actually ought to put really all, and I'll highlight that, all industrial metal extraction happens at high temperatures. Every single one of them. Key thing is we've got to do this at high temps. So it's nice that even though they're not going to be asking you for specifics, what they can do is hopefully get you to realize that that is still a thing. They're going to give you a question with very specific sets of details and ask you to explain really why the conditions are being imparted onto that. I want to give you some questions. So the first question I'm just quickly going to put for you is why are high temperatures needed? Why high temps? Why high temp for iron extraction? So, okay. Now, the first reason for this, and of course, they're gonna give you a diagram, and they could actually ask you, of course, how it's generated, As long as they are giving you it in the context and giving you the details, they can do this. So the first one is in iron extraction, we input 3 things into the blast furnace. So if I just draw the top of the blast furnace here, this is the top of the blast furnace. If I just kind of extend it down, and there's the top. 3 things go in here, and there's our source of iron, which is hematite, which they can still ask you about. There's coke, and that's the important one for industrial. There is also limestone, and limestone's to remove impurities, but the coke is the key one for the high temperatures. Because what we're actually doing is, coke, of course, is a form of carbon. It's a very pure form of carbon. And this is the source of heat. So the carbon burns in oxygen to form CO2, and they can ask you for these equations. As long as they say, coke goes into the blast furnace as a source of heat, explain why. And you would, and they'd say, provide equations for these reactions. So carbon burns in oxygen to form CO2. This is exothermic. And that's going to generate our heat. And then it reacts again. Carbon dioxide reacts with more carbon to form 2 carbon monoxides. And this is our reducing agent. This is our red agent. This is what's going to steal the oxygen from the hematite. And that's our source of heat. And even though you don't need to give specific temperatures, you don't, now in the old days, you used to have to quote 1600 Celsius. That's incredibly high. You don't need to quote that now. What they can do is it requires high heat. Explain using an equation how that heat's going to be generated, but by giving you the products going, the reactants going in, and you'd be expected to be able to translate that out. This is why not deleting these from my teaching is important, because knowing more about these industrial processes makes these exam questions in settings much easier. Won't they give you like one of the products is propane or similar? Yes, potentially they can do. They can tell you what the products are, and that would allow you then, of course, to create your equations. Okay, so again, I just want to just finally finish off with iron in particular for calcium carbonate. Calcium carbonate is limestone. Limestone, of course, is a common name, not IUPAC. IUPAC is the International Union of Pure and Applied Chemistry, and this is chemical name. These are the group of people who came up with the chemical naming system, and of course, the chemical name is calcium carbonate. Now, calcium carbonate, that was really poor writing. Let's improve that. Calcium carbonate. So calcium carbonate is added to remove the, and they can give you this. They can tell you exactly what it's doing. Calcium carbonate is added to the blast furnace to remove the impurities of silicon dioxide. And they will expect you to be able to translate these into formulae. And they'll say, and it forms calcium silicate. They'll probably, now since this has been removed, they'll probably give you the product. And they'll just ask you to complete an equation. So that there is the equation for the removal. And as I said, the questions are now no longer going to be quote this from your knowledge. They're going to give you it and expect you to create an equation from what they're giving you. Now, this makes things a whole lot easier because flat out knowing these things is hard work. You have to, the learning process is just simply repeating them and practicing them. And building something from a question is far easier. Okay. So the next thing I want to quickly do is talk about aluminium. So I'm going to electrolysis of aluminium. So I'm just going to do electrolysis. As I said, trying to keep my notes a little bit clearer so I can share it with people. Electrolysis of aluminium oxide. Now, of course, people used to have to quote high temperatures. Now, you don't need to actually, you could have quoted a temperature. In this case, it's 1,000 degrees Celsius, which is insane. Hence the high temperatures for all metal extraction. And the other condition that you had to mention was cryolite. Now, cryolite is added to the mix. It's not a catalyst. It is used up in the process. What that means is it's a condition that tends to be quoted, and they will ask you for its purpose. How does the cryolite lower the melting point of the bauxite during electrolysis? I can explain that. So aluminium oxide is an ionic compound made of Al3 plus ions and O2 minus ions. The electrostatic attraction between these two is crazy high. It's incredibly tough. So this is by the way, the difference in charges is 5+. What that means is that attraction is going to be crazy high. Very strong very strong electrostat attraction. So how do you now reduce it? You add a compound which has ions in it with a lower charge. So if you look at cryolite, which is sodium aluminium fluoride, what I've got here is an ionic compound made of +1s. Aluminium is a +3, and fluorides is a 1-. So what that means is the attraction between these two is far less. So, and again, also between the Na and the F as well. So we've got a weaker electrostatic, the charge difference is lower, so a weaker electrostat attraction. Electrostat attraction. So what that means is the melting point is far lower. The difference between that 1- and 2- in terms of attraction is massive. So the melting point of this compound is 1,000 degrees instead of 2,000. Melting point of aluminium oxide is 2,000 degrees, just over 2,000 degrees Celsius, whereas cryolite is only 1,000. So adding it into it means that this will melt, and that will dissolve in the liquid of cryolite, hence lowering its melting point. So, by the way, that's some lovely ionic bonding question, comparing melting points by analyzing the ions that they're constituted. That's part of ionic bonding. And by the way, very poorly answered questions at GCSE. So, just to, again, mention, just to come back to it in the industrial process. Industrial processes, and I want to give you a quick couple of really important facts regarding industry. Industrial processes are all continuous. The opposite to continuous is batch. Continuous means non-stop. This never stops. It runs, these plants run for 10 years. Then what will happen to Na and F? Okay, that's a really good question, Sarah. They remain in the solution. The sodium is more reactive than the aluminium, so the aluminium will collect the electrons rather than the sodium. And fluorine is more reactive than oxygen, so won't give away the electrons. Oxide will. Oh, Sarah, you're asking some really, really detailed questions here. So just to explain Sarah's question, here's my electrolysis vessel with the positive electrode, otherwise known as, panic. So panic's always a great one. Positive anode, so that's the anode. Put that in a box. And negative cathode. So this is the neg electrode, and that is the cathode. And so if we now put our ions in place, we've got aluminium 3+, we've got aluminium 3+, we've got sodium 1+, we've got O2 oxide and fluoride. What's going to happen is both of these ions are going to drift over to here due to the electrostatic attraction. So when these guys are going to both fall over to here. So what's going to happen at each electrode is that the ions are going to want to give away their electrons. And here's the thing, because fluorine is more reactive than oxygen, the fluoride will not want to give away its, won't want to lose them. There's somebody who wants to lose them more easily. This was less reactive at its start point. So the oxygen will lose its electrons rather than the fluoride. The oxide will lose its electrons rather than the fluoride. Same thing with the sodium and aluminium. The Na+ and aluminium, the sodium is more reactive, so it will not gain them. That's more reactive, whereas this is less reactive. So the one that's going to take the electrons is going to be the aluminium, and it's going to take 3 of them. It's nice to see our half equations appearing. So at this point, the O2- ions will form oxygen gas, balance for atoms, and hence balance for charge. Everyone gets that number wrong because they think it's 2- and it's not. There's 2 of them, so it's 4 electrons. That's losing electrons, loss of E- because they're being spat out. Out is loss. So oil rig. Oil is the loss of electrons. This is oxidation. And on the other side, the aluminium 3+ is going to attract the 3 electrons and gain them, forming aluminium metal. So this is rig. This is gaining electrons. This is gaining minus. So this is reduction. This is red, and this is oxidation and reduction. And it's just nice. Now, just to tell you, it does get used up. The sodium and fluoride, the sodium ions and fluoride ions will every now and again, because the concentrations are very high, they will every now and again form at the electrodes, but they're in such a low quantity you don't really tend to see them. So it does need to be replaced, give or take, about every 6 months or so. Does it mean the solution would have NaF? Yes, yes, actually, it will actually. It will slowly get used up over time, but the concentration will increase slowly over time. But then, of course, they're going to be continuously adding aluminium oxide to the mix all the time. This is what I mean by continuous. They're adding it all the time without ever stopping. 10 years these run for. Industrial processes are continuous. They're mostly done at high temperatures. Oh, is there any other ones that we want? Any other generals that we want for industrial processes? It's always about trying to get a good yield. Aim to produce high yield. And purity needs to be mentioned, and high purity. This again links me back to the metal extraction and Edexcel's horrible point of, you do not need to know this, but given the information, can you discuss it? Which is really, really mean, because so just to quickly mention that if we extract iron using carbon, I'm actually going to get rid of the carbon monoxide and just put flat out carbon. That does happen as well, but it's in far less quantity due to them all being solids. If you extract iron this way, you form very impure iron because it has a carbon impurity, because we add excess. Carbon's added in excess to make sure we create as much iron as possible, but we get carbon impurities. Hence why it makes steel when it actually comes out the furnace. Now, if you look at another equation, like aluminium extracting via electrolysis produces pure aluminium. This is a really great process. We really like this. I can't not balance equations. It's really bad that. It feels a little bit OCD. But this is going to produce very pure aluminium. And the reason for this is because the only other product that we have coming out is a gas. So the byproduct is a gas, which is going to bubble away. Remember, we don't actually make oxygen, of course, because it reacts with the graphite electrode. But the products of all gases, which means no solids are remaining. So we produce very pure aluminium. This is a very expensive process, super expensive to produce aluminium. You've got to pay for the fuel, for the heat. Fuel for heat, that's expensive. Remember, you don't pay for heat, you pay for fuel. And also, you've got to pay for electricity. Pay for electricity, this is expensive. Just to consider another, now, of course, this, we're going to give you it. Let's just look at one other metal extraction. This is tungsten. Tungsten is extracting using hydrogen gas. Its reactivity is incredibly low. And that produces this. It's done at just under, this is done at 1800 degrees Celsius. Now, this produces exceptionally pure tungsten. And the reason being is because the water comes, of course, at this temperature, leaves as a gas. Same reason as I can't not balance it. It's really freaking me out. There we go. So the tungsten, once again, comes out incredibly pure because we're putting in a gas as the other product rather than a solid, and we're creating a gas as our byproduct. So we get an incredibly pure tungsten at the output, which is, by the way, useful considering we use it for light bulbs. And if you want a light bulb to glow, you need it to be very, very pure. Otherwise, it will reduce its conductivity, hence its efficiency. Okay, so I kind of feel like I can box off the metal extraction at that point. Next thing I want to do is, I just quickly, again, it's always nice to do the reminders of this. The next one I just want to quickly mention is crude oil, is fractional distillation. This process, you can pretty much now guarantee to be on your paper 1. Now, that's awesome. The problem is, guys, year 11, guys, you really need to learn this story. And it is a story. And I'm sorry that it has to be bulk learned. But please, please, make the time, make the effort. So, crude oil vaporized. So once we've vaporized it, and I have to mention it because it's done outside the tower, we feed gas, feed vapor into tower, by the way, actually all you need to say is tower. You don't need to say fractional distillation tower or fractional tower. Then you can do tower has a temperature gradient. I always like now to explain that gradient. Hot bottom, warm top. Please make sure you don't put cold. This is important. It's not cold, it's 60 degrees. That's very hot. Next, bigger molecules have higher boiling points. Bigger molecules have higher BPTs, higher boiling points. Right? Why do they have a bigger boiling point? Bigger molecules have stronger WIMPs. And that's nice to see a covalent mark coming in here. Have stronger WIMPs. Now I'm putting in WIMPs. You're not allowed to write that in your exam, so I will translate weak intermolecular forces. WIMPs is great because it's easier to remember, and your brain tends to be pretty good at being able to translate this out. So definitely worthwhile practicing that. And it's a great covalent bonding because these are all simple covalents, of course, in oils, hydrocarbons. So bigger molecules, sorry, I've missed a word. Bigger molecules have stronger weak intermolecular forces. Bigger molecules condense lower in tower. I always remember, the only ones I really remember in the tower is bitumen at the bottom and natural gas at the top. Do we need to know all the individual chains? Kayun, great question. No, but what you do need to do is be able to name the fractions. That will be asked. They've cut industrial chemistry down to 4 processes. They're going to give you this. Let me quickly show. I'm tempted to actually show you straight from the specification document, from the specimen exam paper. But what they're going to do is they're going to give you this tower, and I'm just going to do it this way. Give you the tower and ask you what comes out at these different points. So fraction 1 at the top, so we've got natural gas. Fraction 2 is petrol, or commonly referred to as gasoline. I don't know. I was going to go Yorkshire. I don't know why they keep wanting to use the American term gasoline. They've also called it petroleum gas. Every single one of these has appeared in an Excel paper. So do watch out. Next one is natural gas, petrol, naphtha, used for cracking industrial processes, industrial chemistry. Naphtha, kerosene, jet fuel. By the way, and yes, just to warn you, they're going to ask you for the uses of these, and be aware that car fuel for petrol, kerosene is jet fuel. You can't just write fuel. Be aware of that. This is car fuel. This is car fuel, and this is jet fuel. Not the same stuff. Can't just stick it in any vehicle. Followed by diesel. Car fuel again. Nice to put car fuel back in. Followed by, this is usually lubricating oil, but sometimes lubricating oil. Sometimes put in as fuel oil. And the very bottom one is bitumen, which is used on roads. By the way, fuel oil or lubricating oil is fairly expanded. Fuel oil is power station fuel, or boat fuel, power station fuel. And bitumen is for road surfaces, roads. So yes, they genuinely will ask you for those. And what they're going to do is they're going to leave a blank one. Most common ones for them to leave are naphtha and kerosene and bitumen. Those are the usual ones they leave out, and they go, fill in the blanks. So do be aware that they're going to do that. And longer chains are at the bottom, shorter chains are at the top. Bitumen C50, got 102, it's massive. It's got a variety of ones in it. Natural gas, of course, being C1 to C4. At this point, I am going to now mention the fractions. There is a definition that's going to appear, and everyone tends to get this wrong. A fraction is a group. A fraction is a group of compounds with similar boiling point, BPT. This is why in the gas fraction you get C1, so methane, and C2 ethane, and C3 propane, and C4 butane. All of these are in the gas fraction, or in the gas frac. Whereas petrol, as another nice one, petrol fraction contains C5 to about C10. C10 is fairly common. Commonly referred to, by the way, as octane. And this question has been asked, why would you call the petrol fraction, why would you call it octane when it contains all 5 of these compounds? And the reason being is, of course, octane is the most abundant in the mix. So it's nice to just to refer back to our fractions, and they do appear quite a lot. Cool, so that covers our fractional distillation of crude oil, so I can tick off those two. Right, next one, cracking. By the way, please, it's nice to also notice them carrying on a theme here of organics. So organic chemistry is really being hit hard on industrial. Basically, they left in the industrial processes for the organics, but removed it for all the others. So next one is cracking. Now, please note, on your specification, they have dedicated numbers. So you need to know that the cracking process is done between 600 and 700 Celsius. So, by the way, I quote 600 because it's an easy one to remember. And it says using a silica, I'll highlight it, a silica alumina or alumina catalyst. Can I just point out, I hate Edexcel for that. The reason being is those of you who will go on to do A-level chemistry, so let's just give our conditions, 600 Celsius, and I'm going to tell you to learn a zeolite catalyst. And the reason for this is because at A-level, you're not allowed to quote aluminium oxide or silica. Silica's sand. It's not a catalyst for cracking. They're just trying to simplify it down. And at A-level, you will have to quote zeolite. So just learn the right one. And on every single mark scheme, you will notice it is in the allowed section. Keep it, year 11. So it's nice to mention it, but I will at this point, want to drop in to catalysts. And the reason why is because in your notes, in your specification, they're quoting 2. Why would they quote 2 catalysts? And in reality, if I actually give you all of them, it turns out that there are 3 alumina. By the brackets, aluminium oxide, Al2O3. So they're mentioning 2 different catalysts, but in reality, there's 3 of them. And that's the top one. That's my favorite. That's the most important one, zeolite. But why would they mention 2 specific catalysts? Because what they're going to do is they're going to talk to you about the differences between them and why you would choose one catalyst over another. Now, at this point in cracking, I'm going to quickly show you. They can also ask you, because this is one you have to know. They can ask you to draw the experiment for cracking. Now, year 11, I haven't actually done this with you guys in lesson because we had a major problem with equipment on the day that I was trying to organize it, but I will do this as soon as we finish our spec next week. I'm going to get you guys just to do practicals and make sure that we know those diagrams. And this is one of them. I'm going to draw it for you, and then I'm going to show you the picture from the internet. So here's a boiling tube. Please note, year 11, this is a boiling tube, not a test tube. People keep getting those mixed up. A boiling tube is for heating. A test tube is for small-scale tests. You then have a piece of glass wool. Now that glass wool is soaked in paraffin. Soaked in paraffin. Now paraffin is the common name for diesel, which is, I think, is kind of cool. So we're actually soaking this in diesel fuel. It's a little bit thicker than diesel. Diesel, they add another chemical to actually thin it, but it is the same length of chains. So give or take around about C16, H, double it and add 2, 32, 34. So you add in paraffin. Then what you have is you have a catalyst. So here's our zeolite catalyst, which we add. Zeolite or alumina or silica. What we then do is we then put a cork on the end of it with a delivery tube on it. Now I'm just going to quickly erase that line because I don't like the idea of sealing that. Now I have seen some really, your screen's gone. I see Mr. Duncan's head. Oh no, has it cut me off? Oh, so sorry about that, guys. Let's try that. I don't know why I decided to unshare me. Thanks for letting me know. We see your ceiling. Excellent. Is it back? I'm hoping that it's going to be back. I must have hit hide. I must have hit the stop share button. Okay, so going back to this. So there are 3 different catalysts, and they're going to ask you to compare them. Now, I have seen some ridiculous diagrams of this, and I'll explain them in a minute. But this is a delivery tube. Now, the delivery tube, I'm going to try my best here. In an exam, of course, I would still try my... Oh, don't like that. Let's get rid of that. Go away, go away, go away. There we go. There's my ridiculous delivery tube. And we collect this underwater. So we're going to get bubbles of gas. And then the boiling tube, of course, or the test tube then to collect it in is also full of water. And the gas then builds up at the top. This is called fluid displacement gas collection. And that's your diagram right there. And we now heat this. We heat the catalyst and heat the oil. So we heat both. I don't like how difficult that is for me to do there. There we go. So we heat both. And what this will do is the vapor of oil, the first thing the oil will do is the oil will turn to gas. From liquid to gas. Then it's going to pass over the surface of the catalyst. As it passes over the surface, it's going to crack into its shorter chains. So it went in as a 16 long carbon chain, and I now get a shorter alkane and an alkene. Now the alkene is going to come out as a gas, but the shorter chain will come out of oil, will come out as an oil. So what you tend to find is, you tend to find that you end up with the gas. With the gas, of course, collects up here. Here's your alkene gas collected. And what you then also tend to get is little droplets of oil all over the place. I should do that in like a different color just to make it look like oil. And that, of course, is our shorter alkane. So in this case, we've lost the oil. So I just wanted to show you that it can be drawn in a reasonable amount of time. However, it is rare for them to ask this, and what they will tend to do is give you the diagram. So I thought that I'd quickly show you, and it's nice just to also highlight the porcelain chips. Porcelain or clay pot or clay is zeolite. So this is the catalyst in this case, and they've given you the diagram, and you can see they're doing exactly what I drew before. I've also seen a variety of pictures with this, including where the bung didn't fit. They gave a diagram where the bung was actually the wrong size, and they asked you to identify the problem with the setup. I thought this was quite clever because, of course, what that means is any gas we make will escape out the edges. Do watch out for these. Look at this picture and tell us what's wrong with it. I've also seen a version where the boiling tube was not underneath was not above the delivery tube, which meant the gas would escape outwards to the side. So there were lots of these little subtleties, and these pictures can be they can give you what's the problem, etc. And they can also draw, and they can also go, oh, here's another one. A Bunsen valve fit here if desired. I now need to specifically talk about this practical and its dangers. There is a second version of this, by the way, which has appeared a few times. Same thing, I apologize for the poor quality of the diagram, but in this time, what's happening is, as the liquid passes over, the long chains pass over, and I get a liquid, remember, I get a liquid oil, a shorter chain alkane, which is a liquid. And that liquid has dropped down into here and into a cold water bath, which is going to help it condense. Are we allowed to put zeolite for the cracking catalyst? Because I remember doing a past paper that allowed. Yes, that's correct. So Sarah, it's not the top answer they want for EdXL, but it's always in the allowed section. And I want you to learn it because it's the only one that's allowed at A level. And I don't like teaching you chemistry that you're going to then have to I have to say, you're going to have to unlearn this. Just learn it right the first time. So you can always choose zeolite. It's the correct answer. I don't know why they decided to delete it. What they decided to do is make it easier, and so something that you might have already seen before, aluminium oxide or silica as sand is one that you've already seen. But they're trying to make it easier. They're removing content on this, and I don't approve. So stick with zeolite. So they're going to ask you, explain the cold water bath, and this is going to condense the liquid. Cool. It's going to cool and condense the liquid. Condense the alkane into liquid. So then, because the alkene is very short, the alkene, of course, which is incredibly short, being usually 2 or 3 carbons long, won't condense into a liquid. And that gas will then pass down here and will collect in our tube. So this is a far better method, and it prevents some of the dangers. And I've seen all kinds of things, all kinds of bizarre things with these diagrams, where the tubes were too long. If the tube went down here all the way into the water, you push the water up the tube, all kinds of bizarre things, but they seem to keep it a relatively simple at GCSE, even though that's not a particularly simple diagram, and hence why they don't tend to push you too hard on it. Okay, so the next thing I want to mention at this point is I'm going back to this version, and I need to now mention a very specific practical hazard. So this is a hazard for the cracking practical, and this is called suckback. Yes, it's very entertaining, I know. So suckback, I'll quickly explain. What you're doing is you are producing a very high temperature gas here, a high temp gas. Now, gases at high temperatures, when you raise their temperature, they will expand. So, and this question has also been asked, why don't you collect the gas for the first 2 minutes? Because the first gas that's going to bubble up is going to be air. First bubbles produced are air. And that's the air that was in the tube originally. Air in tube that's expanded. Right. So after a few minutes, we start collecting it. Now, here's the problem. This gas is very hot. So what will now happen when you stop heating? When you stop heating, the gas in the boiling tube will cool. When you stop heating, gas in boiling tube will contract. It'll contract, it'll shrink in size. Now, what that means is that the water, the fluid at this point, don't like red, too dark. The fluid that's in contact with that tube will start to get sucked up the tube. And it's actually terrifying when you see this, Because if that water reaches the top and it gets into the tube, then the tube explodes. This is because as soon as that cold water hits the tube, which is probably at about 300 Celsius, it instantly flash boils, turns into a gas, and the whole thing explodes. And you've got boiling hot oils exploding into air, which will probably catch fire at the same time. So when you stop heating, gas in boiling tube will contract. Water will get sucked up. Water sucked up can cause explosion. Can cause explosion. So how do you prevent it? They like this question, and it's really easy. You remove the delivery tube. I'll give you the question here. How do you prevent suckback? And that is very easy. Answer: remove delivery tube from water before you stop heating. Not complicated. It's common sense. And they have asked it on several occasions. So that pretty much sums up cracking in terms of the industrial process. You quote the catalyst and you quote the temperature. Next, right, so I can tick off cracking there at that point. Okay, here's the big one. Right, I'm into paper 2. Dual scientists, you may leave. And we're into ethanol. So, okay, now this is 2 industrial processes sandwiched into one. So, into the same topic. I'm going to find another space. I keep getting further and further to one side. I'm not entirely sure how that's going to like that. So we can now talk about the industrial. This is the production. See if I've got any questions. My laptop's gone to sleep. Okay. Are we allowed to put zeolite? Yes, we are. Glass everywhere? Yes, absolutely. Okay. So production of ethanol. Now, there's a whole load of nice things I want to comment on this one. It's part of organic chemistry. The first thing I want to do is quickly mention some formulae that you're going to come across and you're very likely to see in your exam. The first one is C2H5. I hate this formula, but you're probably going to see it, so please recognize it. What they're trying to highlight here is 2 carbons, hence F, yeah, and then the ol group. So they're expecting you to be able to recognize that because of those 2 points. But I hate that formula. You should never use it. They can, but you can't. The next one is the proper formula, which is CH3, CH2, OH. This is called a structural formula. This is a written structure, structural form. Next, that's the correct one. The next one is displayed. Gotta love displayed. Now, displayed means show all bonds. And I'm now going to deliberately make a mistake and put it to the classroom. Why have I lost that mark for a displayed formulae? Who's going to get there first? Thank you very much, Dana. Absolutely spot on. The bit that loses you the mark is the OH, because the words displayed formula is a drawing showing all bonds. And it's the internet's fault. I blame the internet entirely. Miss Alday said I can put it without a line. Lucas, don't. Please don't. It is not good chemistry. Please don't. So it's a very, very bad habit that you shouldn't start now, and they can penalize you for it. If they ask you for displayed, show that bond. I really cannot stress that enough. Please, 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 emphasis, show it. Yes, this is good chemistry. Okay, so at that point, it's nice just to quickly mention the different types of formulae we see. By the way, if I was just to do the molecular, C2H6O, the molecular formula is just counting everybody. Molecular formulae. That is the number of atoms of each element in a compound. And in this case, I've got 2 carbons, I've got 6 hydrogens, and I've got an O. The empirical is the simplest whole number ratio, empirical form, and that is the same for ethanol. The reason being is the oxygen is already at 1. That's the reason why that is the empirical formula. So they're the same. It's okay. They have asked it. They have done that many times. Okay. Next part. Let's now go on to its production. So 2 industrial processes. So to make ethanol, which is alcohol, of course, and if they ask you for a use, it's a fuel. Don't say we drink it. There are 2 industrial processes you need to be able to quote. The first one is called fermentation. Everyone knows this from biology. And the second one is called direct hydration. Once again, we are now down to 4 industrial processes, folks. You can guarantee this is going to appear on your paper too. So learn them. So fermentation. This, of course, is using plants. Let's just initially quote the conditions. So we can do fermentation. Conditions are 35 degrees Celsius. It is no air. It is yeast catalyst. And you're done. There's your conditions for fermentation. Now, they're going to ask you about every single one of these conditions, folks. So I'm going to come back to direct hydration, and I'm going to focus on fermentation. Number 1 question. Why 35 degrees C? This question's actually, this whole 35 degrees are very frustrating because the questions are a nightmare because there's a few of them. Why 35? And by the way, this is important. Why? And that is optimum temperature for enzyme activity. Next, if it would ask for 2 reasons, that's the top reason, our survey said, top. And we could also say, by the way, Amira, you can't just say optimum temp. It's not enough. You must say for enzyme. If they ask you for 2 reasons, optimum temp for yeast growth. That's the second one. But the first one is top answer. If they want one, quote that one. You need to quote that one. That's the top answer. Okay, so why not 55 degrees Celsius? And their answer is enzyme would denature. Enzyme denatures above 35. Nice to see that. Yeah, denature. Lucas, you're doing great. I like it. Why not lower? Why not 25 degrees Celsius? Put it out to the classroom. Why not 25? How many people are going to say not optimum temperature? Lose your mark. Not allowed it, folks. Why not? It would work. Active sites not, like enzymes are inactive. Nope, it will do it at less than 25. Sorry, at less than 35. Absolutely will. And that's the point, isn't it? Slows down. Well done, Dana. Spot on. Slower reaction. Produce alcohol, ethanol produce less ethanol per unit time. Company makes less money. Less money. And they've done it. By the way, I'm going to now at this point highlight the less money. I have seen this, and it's very easy for them to push you into this. If they use the word question, give and now I change my color, economic. Give an economic reason. They want a reference to money. Business and chemistry, absolutely. Economic, given an economic reason, full stop, you must mention money in your answer. It must be about profit, usually. Cool. Okay. Next. I've suddenly realized I've skipped my different catalysts question, and I'm going to have to come back to that. So direct hydration. Let's look at the equation. I take ethene. By the way, and at this point, I'm going to make a really quick mention to bond numbers. Please remember, carbon makes 4 bonds. The most common mistake that I keep seeing in an exam, which drives me crackers, is that. Please don't. That carbon, let's highlight a carbon. This carbon now has 1, 2, 3, 4, 5 bonds. That's too many. Please don't do it. Yeah, same with this one. This one has got exactly the same thing. We've got 1, do it in blue this time, 1, 2, 3, 4, 5. Too many. Please count them properly. This is wrong. Ethene. Oh, gonna make a bit more space. Ethene. We're gonna take ethene, and that's a gas, and we are going to put in that's displayed. Let's put it into structural. CH2, CH2. Let's put it into molecular. C2H4. You can get any one of these, folks. And we're gonna add steam. And by the way, this is important. If they ask you for the words, you're not allowed to say water. Be careful. Add H2O, and that must have a state symbol of G. It must. And what am I now going to make? Notice it's in equilibrium. This is now the only equilibrium that you need to know for GCSE chemistry. But that doesn't mean they're not going to ask you for others. I'll mention Haber shortly. Okay, so there's our ethanol coming out. If I give the proper one, CH3, this is structural, followed by C2H5OH. That's what they're going to do. So all of these are the same, and we now need to give very, very specific conditions. So this is done at 60 atmospheres. Now that requires explanation, because if I now say to you guys, and they're gonna do this, you can guarantee it because there's so few industrials now, they're going to say, in terms of pressure, I'll put it out to the classroom, Mr. Duncan, gotta go. We'll re-watch this for further notes. Thank you. No problem, Mira. So guys, here's the question to you. In terms of pressure, do I want to raise it or lower it for more ethanol? Do we raise pressure or do we lower pressure? Which one? See the first person who gets this right. This is definitely grade A at this point, by the way, folks. Which one? Raise. Absolutely right. Lucas, room in. Raise is correct. Dana, raise. Lucas, raise. Excellent. Less moles on the right. Outstanding, Lucas. Well done. Love your extra detail there. Exceptional chemistry. Well done. There is one over on this side of the equation. Over on that side, there are 2 moles of gas. And on this side, we've only got 1 mole of gas. And high pressure, oh, too dark, don't like it. High pressure will favor less moles. So it'll shift it over to the other side. So it'll shift it that way. So we should, and we can go above 60. 60 is easy. God, 60 is like a walk in the park. But we can't go any higher. The reason. Question, why not higher pressure for better yield? There is a very distinct answer to this industrial process. And the answer to that question, this is the question, the answer is the ethene at higher pressures will polymerize. It'll turn into plastic. And we're not trying to make plastic here, folks. What we're trying to make is ethanol. And by the way, that happened once in the 1980s in a big power plant in the US, and the whole plant exploded, killed like 11 people or something. The reason being is all the pipes got blocked by the solid plastic that formed. A valve got stuck, pressure went up, ethene polymerized, turned into polyethene and blocked all the pipes, and the whole plant exploded. Not good. Next condition we need is we have to quote 300 Celsius. And this, oh, it's going to appear. So once again, I'm going to ask a question. So, question. The forward reaction, in fact, I'm going to give you exactly as they would. Question. C2H4 plus H2O goes to in equilibrium to C2H5OH, and they're then going to give you this minus, oh, can I quote that number? Something like minus 46 kilojoules per mole. So the question is, what does this tell us about the reaction? Put it out to your year 11. What does that tell us about the reaction? First person to give me an answer. Well done, Donna. It's in what direction, Donna? In what direction? Well done, Donna. Spot on. Forward reaction is exothermic. I'm going to do that as an arrow. The forward reaction is exo, and therefore the backward reaction is endothermic. So that's endo. So what do I want? If I want to get a greater yield, increase yield, what do I want to do to the temperature? Do I want to raise or lower? Question, out to the class. Decrease. Well done, Lucas. I want to decrease the temperature. We're going to lower it, folks. We're going to lower the temperature because a lower temperature will favor the hot reaction, the exothermic reaction. And they're going to do this to you. So lower temp will favor exo brackets forward reaction. Equilibrium shifts from left to right. Increase yield. Shift L to R. Increase yield. So why so hot? Next question. So why 300? Seems awfully confusing. Why would you do 300 when we could lower it? Take it down to 100. Take it down to 10. Stuff it. Let's take it down to minus 50. Well done, Winkit. By the way, Winkit, you're right. It does. Can you give me the other word, please, without me saying it? Give me the word. The one word I need. Donna, that's rubbish. I didn't say the word economic. Never ever mention cost unless they give you the word economic in a question. Because we don't know. The word begins with C. Who's going to get there first? O. Come on, folks. M. No. P. Winkit, your answer was correct the first time. No. It's giving you up. What? Donna? Computer. Oh. Compromise. This is a compromise. Thank you, Winkit. Saved the day from Dana giving me concentrated and computer. You just gave me any word that began with comp. Nice one, Dana. That was hilarious. Answer of the day. Definitely give you a commendation for that one. It was awesome. Compromise. So we want a reasonable yield and a reasonable rate. It's the medium. It's the one in the middle. But that, don't forget, that's a mark. You've got to use that word. Have to. Reasonable yield, reasonable rate. And they're going to do that to you. Cool. There is also a catalyst, folks. So the catalyst is concentrated, and you can't miss that. Concentrated phos. Oh, hang on a minute. No. That's us. Oh, concentrated sulfuric acid. For this one, concentrated sulfuric acid. Yeah, that's correct. And it's important that it's concentrated, folks. You can't be dilute. It doesn't work if it's dilute. At this point, it's nice for me to just remember to do a bit of kinetics and just talk about a catalyst, because of course everyone forgets. A catalyst has two questions. Question number one: what is a catalyst? What is a cat? Meow. Can someone give me the answer to my question, please? What is a cat? What is a catalyst? Answer. What is? Oops. A substance that doesn't get used up and lowers activation energy. Dana, you just lost it. A substance that increases rate of reaction, but itself, but I'm just going to put, but not used up. Lasts forever. Why does a company use a catalyst of platinum even though it costs such high amounts? Because they only need to buy it once, and it makes them money, more and more money every single time. Yeah, the second question for catalyst is explain how a cat works. Not the same question. Answer. It provides an alternative route of reaction, provides alternate route with, that's your key word, with a lower activation energy. Cool. Just watch out for those. Okay. At that point, we are done with industrial chemistry. Oh, got another diagram to show you. This one appeared in an exam once. And they actually gave you they added ethanol. This is actually the opposite. They reversed it. I thought this was genius. It creates an alternative pathway, yada, yada, yada. So because this is also an equilibrium, it can be reversed. And they did a genius question. I wish the exam paper had color. I know, right? They reversed it, and they gave you this diagram, and they added ethanol and concentrated sulfuric acid, and they heated it up, and they collected the ethene. And all the question was asking was to give the equation. And I thought it was lovely. They gave the picture. They also said what was the purpose of the thermometer, and that's to read the temperature of the ethene gas that's being made. So the question was give the equation, and of course it was genius because it had reversed it. You had to take ethanol, CH3, CH2, OH, break it apart with conc H2SO4 as the catalyst, and you formed ethene and steam. Genius question because they'd reversed it. Really nice. Why don't you see the water? Because the water dissolves into the water bath. Thought that was dead nice. Thought I'd show you the picture. Right. And at that point, just to quickly mention absence of air. For fermentation, why do you need the absence of air? Because the yeast will turn it into CO2 and water instead of ethanol if there's air present. Okay, that finishes all of our industrials. Let's quickly run through our paper, folks. Right. So, nice to see. This really has focus. These are real questions from exam papers, and of course, the big focus is on organics now. Say what is meant by the term isomers. Molecules with the same molecular formula, but different structural formulae. Next, and by the way, nice to see this one. Why are these two here isomers? They're isomers. Don't know why I did that. They're isomers because the top one is, let's count them. 1, 2, 3, 4. So that's C4H. 1, 2, 3, 4, 5, 6, 7, 8. That's C4H8. Let's count the next one. I've got 1, 2, 3, 4 carbons, which is C4. And H's. 1, 2, 3, 4, 5, 6, 7, 8. Right. These are definitely isomers. They have the same molecular formula. Same molecular. However, different structurals. Here are your displayed, which are completely different. Yeah? One of them at the top has a double bond, and the one at the bottom, one at the top has a double bond, the bottom doesn't. That's cyclobutane, and then, of course, butene. But they are definitely isomers. Same molecular, different structural. It's nice, that. So, next, draw the displayed structure of another isomer of but-1-ene. Now, what you've noticed is that I've answered it, and I've actually got, well, I wanted to show you it actually moving. Students often miscount the bonds, but what we need to realize is that there is the original picture. So how can I create this as an isomer? I need to change the structure. So what I'm going to do is I'm going to move the double bond. I'm going to get rid of that one. My pen seems to have died. I don't know why. Oh, it's not letting me erase that for some reason. Oh, my board is having a break. It's having a hiccup. Right, so what I want to do is I want to move the double bond. So I'm going to break off that double bond. I'm going to put it in the middle. Now, if I do that, I'm now going to have an incorrect number of hydrogens on this guy. So I need to delete somebody. So I delete that hydrogen. This one still has 1, and then the one on the end now gains an extra. So this is now but-2-ene. I have moved the double bond into between the carbon 2 and carbon 3. I'm just going to show you this next to this guy. So this is where the double bond is originally. So the double bond originally is between carbons 1 and 2. And what I can now do is move it to carbons 2 and 3 and count on my H's. Most people will throw away this mark by attaching hydrogens to this guy. Please don't. Be careful, folks. 4 bonds, remember, that's butene. It's a different isomer. Next. Describe the test to distinguish between but1ene and cyclobutane. Well, this is the test for the ene family. So I'm going to add bromine water to a sample of both but1, and then it will turn it from orange to colorless, and cyclohexane won't. By the way, I've missed something there, which is you always have to do the color before as well. So I turn it orange to colorless. That's what it's going to do for the bromine water. And then I thought I'd show you the reaction. The cyclohexane won't, because it doesn't have a double bond. And you can see the reaction I drew out. I've got ethene. I haven't bothered with butene. I've just gone and done ethene. But I've got ethene here. And you can see I've just swung the H's up to make it a little bit easier to see. And I've got orange bromine highlighted in yellow. That's going to attach itself and break the double bond and form colorless dibromoethane. Next, I thought I'd show you this one again. But1ene and steam. Now, guys, this is what I mean by industrial chemistry and giving you different ones. Even you've studied one, so you can do the others, which is a nightmare. So in this case, I've tried to label everything. The yellow hydrogen's the one on that carbon. And what I want to focus on here, folks, is the water. Look at the water in red. Just going to draw water out in terms of its bonds and show you that when water adds to an ene, it also breaks the double bond and goes across it. And we're going to break it here to break off one of the H's, and the OH goes onto one carbon. I'll just highlight those now to make it easier to see, to be fair. My tablet is still hiccuping, still not doing what I want it to. Really isn't doing what I wanted to. Oh, I drew a picture there. We break the water in half. The O goes onto one carbon. The H goes onto the other carbon. And then we also break one. I'm going to make that a bit clearer by making that bond further apart. We break one of the double bonds. One of those breaks, and they go across it. Just like that. Clever that. Polymerization for you 11s who I haven't done this with yet. Our last topic to do. The polymerization, poly means many, mer means part, and ization means joining, adding to something. So many parts adding together. So we take any number of these, any, just see that, sorry, I'll stop. We take n numbers of but1enes. The double bond snaps open on either side, which is this bit, snaps open, and they join together into one giant chain. And I just copy across the pieces that are attached to it and add brackets and n. It's rather nice for polymers. Right, nice to see some nice easy industrial questions. Now this is what I mean by you don't have to be given, right, I'm going to show you which ones they can ask, which ones they can't ask now. So they can ask this one. The double line means a reversible reaction. I think everyone will have this one. The delta, I thought this was genius. They ignored the H, they just gave you the triangle. This means change in. Right, this is no longer required for Edexcel. So no longer requires, this is the vanadium pentoxide catalyst used for step 2. No longer required, so you don't need it. It then says state the temperatures for steps 2. You don't need these either, so they're gone. Next, state why sulfur trioxide, this they can ask. Sulfur trioxide is not dissolved in water to form sulfuric acid in step 3. Why would you add in another step? Well, the reason is, if they ever ask you this and give you an equation, the answer is in the data. It's in the equation. In this case, here. The answer is in the question. That is very, very exothermic. It is going to generate a massive amount of heat and boil the acid you're going to make. You're going to make an acid which is going to dissolve everyone's face off. Not ideal in industry. So we do the steps in this 3-step process instead of 2 because it produces less heat and it's therefore less dangerous. Next, right, they can also do this. Give an equation from steps 1, 3, and 4. They can do this because, guys, you didn't need to know it. Everything was here. Steps 3 and 4. So how do I create step 3? Step 3 is the arrow. So I just go, I need to make, I just take everything out of the data. And what did I put in? I put in these guys, SO3 and H2SO4. And I'm done. H2SO4, there we go. Right, what about step 4? Step 4, I put in that guy and water. So H2S2O7, otherwise known as oleum, add water, and I now get H2SO4. And how many people forget to balance? The first one didn't need balance, it all adds up. But the second one did, and that everyone will miss. So watch out for your balancing. If you write an equation, always check it's balanced. Give 2 industrial uses for sulfuric acid. They can still do this, making polymers and making fertilizers. You can also do making explosives if you wish. Next, again, this is now definitely on your spec. Identify one raw material that's used to make used as the source of glucose, sugar from fruits. Give the catalyst for reaction 1. Okay, concentrated oh, hang on a minute. Reaction 2 uses a catalyst zymase, which is present in yeast. Identify a catalyst for reaction 1. Concentrated phosphoric acid. Oh, hang on a minute. You can use either. I make a mistake. It shouldn't be phosphoric. It should be sulfuric. You can actually, just so you know, you can quote either. I think in industry they actually use phosphoric because it's less damaging to their equipment, but you can quote either. In both reactions, it's important to control temperature. State why it needs to be kept below 35. It will denature the enzymes. We had that earlier in the lesson. Right, a manufacturing company plans to build a factory to produce ethanol on a large scale. The factory will be near an oil field. Oh, well, blimey, guys, they're smacking you in the face with that one. Suggest why the company should use reaction 1 rather than reaction 2. Reaction 1 produces pure ethanol, whereas making fermentation is disgustingly dirty. It's very impure. It's also slow and batch. The reaction 1 is continuous. It never stops, whereas reaction 2 is batch. You have to do it repeatedly over and over, and it's very slow. Factory is near the oil field, which means you have a good supply of alkenes. And the reaction is much faster compared to fermentation. Loads of really good answers there, many you can choose from. In the future, it may be necessary to convert ethanol into ethene. Write the equation, there it is, folks. And give the name of the reaction. Dehydration. So it's nice now to mention if that one here, if that is dehydration, then that is hydration. It's nice to see that name being used. Adding water. Next, fractional distillation. First one's crude oil is heated. That's fractional distillation. The catalyst may be used. That's cracking. No catalyst for practice. Alkenes are formed. That's cracking. Decomposition occurs. We don't want to smash the oils in fractional distillation. That's a waste. Fuels are obtained, that's fractional distillation, and separation is its main portion, is practice. Right? Give the formula, the molecular. Oh, isn't that nice? They've given you structural. So that's a structural formula, and they're asking you to convert it into molecular. Just count the atoms. C5, H12. Then they're asking you to convert it to a displayed. And then, wow, they've gone everywhere. They've gone structural to molecular to displayed. And then displayed, and then, wow, I totally forgot that they did this. And then into empirical. They've done a lot. That's lovely, that. Show all bonds. Just made a note on that one. Give the name of the compound, pentane. General formula, CnH2n plus 2. Remember, that addition there is for alkanes. If it was alkenes, it'd be CnH2n. Balance the equation, pretty easy, but people can't count oxygen. Do watch out for your oxygens. There are 2 in each carbon dioxide, and you've got 2 of them there. So 2 CO2s is 4 O's, and then 2 waters is 2 O's. Total is 6 O's. I need 6 O's, and I get that by having 3 O2s. Do watch out. Draw a dot and cross. Nice to see covalent bonding appearing here. You draw, whenever you do dot and cross, you draw your stick picture, because that's easy. And then you draw your circles. And then you put your circles around them. Carbon, carbon, hydrogen, hydrogen, hydrogen. And then you put on the dots in the gaps for every stick. One stick, two sticks. One stick, oh, put it in the gap, two sticks, one stick, and we're done. Put them in the gap. So nice that, to convert sticks into dot and cross Lewis diagrams. Right, state the process, state the catalyst, concentrated sulfuric acid, and a temperature of 300. They gave you a nice, easy moles question. I like this one. They told you 20 moles. They told you 20 moles, and you just go, oh, I had 20 moles of ethene. What's the ratio? 1 to 1 to 1. That means if I had 20 moles of that guy, then I'm going to make 20 moles of that guy. That's easy enough. So there was the answer, the moles of ethene. Oh, so 20 moles of ethanol, sorry. We're going back the other way, but it's still 1 to 1. And then, so hang on, sorry, 20 moles of ethanol. There we go. Still 1 to 1. Then V over 24, reorganize your equation, and just don't forget to put your number. Don't forget to put your number on the line. Easy mistake. Haber, you are not now expected to quote conditions, but they can give you a picture like this, a process picture. Explain why nitrogen is described as an element, but ammonia is described as a compound. Isn't that a sneaky way of asking you for a definition of an element compound? Element, made from only one type of atom. Ammonia, made from two different types of atoms chemically bonded together. Give the name of gas. X is hydrogen. Its raw material is brine or water. The electrolysis of brine, water. Give the name of the catalyst. No longer on your syllabus. Gone. What is the purpose of why? That, they could ask, is a catalyst. Name the type of a reaction between ammonia and sulfuric acid. Remember, folks, it's nice to me to mention this. Ammonia is an alkali of pH 11. And if you add an acid to it, acid and base, acid and alkali equals salt and water. But in this case, this is kind of special because you don't make the water. Hence why they always ask it. You get ammonium sulfate. Why? Because the ammonia becomes ammonium, which is NH4+. The sulfate becomes SO4 2-, and we need 2 ammoniums for every 1 sulfate. Watch it. Formulae, of course, grade A. Name the salt. Any acid and alkali, by the way, is a neutralization. Next, ammonium sulfate is our formula. Describe a test to show the solid sample contains ammonium ions. This is chemical tests. We did this a couple of weeks ago. Take a sample, add sodium hydroxide and warm. Put damp litmus paper near the mouth of the test tube and it will turn blue. Alternatively, place concentrated hydrochloric acid near the mouth of the tube and you'll see white smoke. Suggest why it is transported as a... Why do you transport things as a liquid? They occupy less space. So you can transport large quantities. We've had the same question, but last time it was just that. Just this time, it was just the triangle, and now it's both. So that now is enthalpy change, rather than just change in. It's now enthalpy change. Forward reaction is exothermic. Low temperatures favor forward reaction. Why low pressure? Quoting moles of gas on either side. 10 moles on that side. 9 moles on that side. Low pressure will favor more gas. It's exothermic in the forward direction. Lower temperature favor higher yield. What do we use ammonium nitrate for? Why do we use it in agriculture? It is a fertilizer. It will increase plant yields. And that brings us to the end, folks. It's a long one this evening. I didn't expect it to be either. So